So good evening you all, one and all here. This is the ninth session of the Numerical Methods for Engineers live sessions on the problem solving. So in this session we are dealing with, in this week or this session we are dealing with the numerical integration. So in the previous week we were studying numerical differentiation. So before going into this week's course, I'll just introduce myself to you. I'm Rigved Saman, PhD student at IIT Guwahati, working in the field of lithium and batteries, and I'm using these techniques for solving my simulations for my PhD studies. So the experience over there should be helpful for you for this course. That's why I'm a TA here under the PMRF fellowship. So for today's session, we are studying a numerical integration. So before going to that, in the previous week we studied about numerical differentiation. So doing a differentiation from the start point, it is a slope of the curve, and from there we studied how to get down to the how we get the Newton's forward difference and central difference formulas, and we studied the error analysis in last week. Today we are dealing with numerical integration. So integration in general is like a differentiation is a slope of curve. A different integration is nothing but area under curve, and area under curve that means if there is some area per se. So from 0 to let's say some value of x, if you consider if you want to find out the integration, you just want to get the area under this curve. So how to get the area under this curve is easy. This basic normal thing is you consider the area of this shape. So what is the area of this shape, you will find out and get to the value. So what in general we do is we get down to the small regions. So we will narrow this region down by some equidistant strips or equidistant intervals, and we will find the area in each curve, so that we will reduce down the irregularities in the curve. So or the curvature of the curve will be reduced down, and it might be a square or a trapezoid on this. So how to get these formulas are about. We start with the numeric so in the course we started with the, if you go into a lecture, so this Newton-Cotes integration formula, it comes out from a Newton's forward interpolation formula. So if you use a forward interpolation formula and its polynomial functions, and you try to integrate it, you will get to the Newton-Cotes generalization formula. For each number of intervals, if you for the different number of intervals, you will get down to the trapezoidal rule, Simpson's rules, or a Simpson's 1/3 rule. Let's say if you have an integration from, let's say, a to b f of x dx, where your a is this and b is this. Alright, so in this case, you will find out the area under this curve, right? So you will take these two endpoints. So this is just a one interval of h. So if that is n is equal to 1, you will get a trapezoidal rule from Newton's Cotes formula. If you use two intervals, let's say you have this h1 as well as h2, then for n is equal to 2, you will get a Simpson's 1/3 formula. And if you use one more interval, let's say if you use 3 intervals, of equidistant h1, h2, h3, and h1 is equal to h2 is equal to h3, in that case you will get a Simpson's 3/8 formula. Alright, so these all formulas comes from this Newton-Cotes formula. That is a generalization formula which is derived from Newton for interpolation polynomials. So the derivation part is already discussed in the theory lectures. So we will go through the numericals and the formulas and then get down to the how to solve them. And even if you have, let's say, what I said for a trapezoidal rule, what I started is, let's say you have this curve and this is your A and this is your B. Alright, what I said, trapezoidal rule, you can only consider a one interval, right? N is equal to 1. N is equal to number of intervals. So you can consider only one interval. Whereas you can always use the trapezoidal rule twice by considering a one more interval like this here. So you will first find out implement trapezoidal rule here and get down to the I1. Again you will find out the implement trapezoidal rule in this region and get down to the I2, and then add them up to get the final interval value. So here there are two steps to get down to the value of I, and similar Simpson's rule can be applied directly with the one formula. So we will go through the formulas and get down to it how to do it. Now this Richardson extrapolation is, so I told you, you can get to the final value of the I using these two for a trapezoidal rule. You can get to the final value of I using two different intervals. Also you can do is, trapezoidal rule can be applied for a one interval also, right? So what you can do is, you can also apply for just one interval of h, this h, and get the final value of I. Now there are some errors in these values to what you got, right? And there is an actual value different. So you will get some value here, you will get some value here, and the actual value or the real value or the true value is different. So to reduce down on these errors, there is this extrapolation formula that has been given by Richardson, which helps in reducing down to the your errors in the analysis, or getting to the better value, getting closer to the true value. So what we do is Richardson extrapolation is, we will find out the value of the integrand using a different interval levels for a same method. For, let's say, for a trapezoidal rule, we will use you will do it for a one interval, then for a two intervals, and so on. And using the extrapolation, you final values that you have got will substitute in that formula, extrapolation formula, and get down to the final value. So that is one method. Gauss Quadrature method is, it's again telling you it's again considering that it's a weighted formula which is derived from your considering your integration is a trapezoid plus so integration is quadrature plus your line. So if you have a line like this, so for this one, so this is a quadrature, and then and then there is a straight this increasing straight line. So derivation part is already done. We'll see how to if we got a numerical, how to solve it. So with no further ado, we'll go to the numericals now. So the first numerical is compute integration I. This is your I integral from 0.27 from 0 to 2.7, 1 divided by 1 plus x square analytically. Then single application of trapezoidal rule, then single application of Simpson's 1/3 rule, then by two applications of trapezoidal rule, and then by single application of 3/8 rule. So analytically you can say, if you see this function, this is a differentiation of tan inverse x. So integration of this is nothing but a tan inverse x, right? So from formula you know, so if you analytically f of, so I is equal to tan inverse x 0 to 2.7, since d by dx of tan inverse x is equal to 1 upon 1 plus x square, right? So if you substitute the values, what will get? Tan inverse of 2.7 minus tan inverse of 0, so the value would be 1.216. So what value you get analytically, if it's a direct method, it's your true value, right? So this is our standard value, or a what is starting called, or this is our I star. We'll always compare the error with this value from now on. That is how we first found out this. So this is our I true or I star. With this we'll compare the other results to get how much closer we are getting using a numerical techniques, and how the discrepancies are come about, that we will see. So this is the first analytically we have done. Now the second question is, solve it using a single application of a trapezoidal rule. So single application of trapezoidal rule. Single application, right? So what it is, just for us this sake, I am constructing this the curve I am going to show is for a demonstration purpose. The curve might be different. So let's say there is a curve like this. So what it is saying, the from 0 to 2.7, so curve might go somewhere from 0 to 2.7 you consider, and find its integrand, means you find the area under this curve. That's what your question is. Now if I call this as a x0, and if I call this as a x1, I can call this value as a f0, and I can call this value as a f1, right? So function value, it's because this is a f of x, right? So these are my values. So what the trapezoidal rule tells you? Trapezoidal rule tells you that, and the distance between this is h. Okay. So how much it is? 2.7, because 0 to 2.7, right? So what is trapezoidal rule is? Trapezoidal rule is for a single interval. So this is a single interval from 0 to 2.7, and trapezoidal rule is your I is equal to h by 2 f1 plus f0 plus f1, right? f0 plus f1. So what is your f1? So for f1, first you should know the f of x, right? So f of x is nothing but your integration in series. So this is I is equal to a to b f of x dx. So this is your f of x. So 1 upon 1 plus x square. Therefore f of 0, 1 plus 0 is equal to 1. F of 1, 1 upon 1 plus 2.7 square, right? So this value is 0.120. Okay, now you got f of 0, you got f of 1. Now you can easily substitute these values here and get down to the final value. Right? Or I'll go with the notation as this. So this is x1 and this is x2. Then we will have to call this f1 and this is f2. These are the, I'm changing these notations because these are the standard ones, that's why f1 plus f2. So basic theory seems the same. So f1 is equal to f of 0, that is 1 upon 1 plus 0, that, or more streamline, f of x is equal to 0, 1 upon 1 plus 0 is equal to 1. f2 is equal to f of 2.7, 1 upon 1 plus 2.7 square, that is 0.120. Okay, so you got these values. Now you can substitute back into this. Therefore I is equal to, so h is 2.7 divided by 2, f1 is 1 plus 0.120. So this will give you I is equal to 1.5128. This is your I value. Okay, if you see the whatever the I you have got from this method is far off from I true, right? So what is happening, it is considering this shape as a trapezoid and finding its area using this formula. So trapezoid rule does that. So but if you see, the area might be different, right, from the trapezoid. So that is why the discrepancy. So the error is, so what the error would be for this sake, therefore error would be, or the absolute error would be 1.216 minus 1.5128, that is 0.2968. So error is quite huge, right? So this, in the scheme of things, might not be the good choice. So let's go for the second one, or we cannot say the values. Let's go for a second one. This one is done, this one is done. Now we are at single application of 1/3 rule, Simpson's 1/3 rule. So for a trapezoidal rule, we only considered one interval. For this is given as by two intervals. So second is Simpson's rule, single application, right? So what is Simpson rule? I is equal to h by 3, 1/3, right? H by 3. So h by 3 f1 plus 4 f2 plus f3. So what is f1, f2, f3? I'll just explain again. Also I'll just explain you now. So what we do in Simpson's rule is, let's say you have a curve like this. This goes from 0 and you want to find till 2.7. In previous case, this was the whole interval. Now in Simpson's rule, we will have a midpoint. So what is the midpoint of this? 1.3 1.35. So this will be your one interval h1, and this will be your interval h2, and h1 is equal to h2 is equal to h, and is equal to how much? 1.35. So these are your two intervals. Now this is x1, x2, x3. Therefore these are f1, f2, f3. So these are your these are your points, and you will again find a whole area under the curve in a one go using Simpson's 1/3 rule. Even if you have two intervals, the area under the curve is found out in the one step. It's one formula itself. You are not repeating the formula in the different intervals. So what you want? f1, f2, f3. So f1 you already know is f of x0 only, right? F of 0, that is 1. f3 also we know, f3 is f of 2.7, that is 0.120. we just have to find f2 f of 1.35. so our function is 1 upon 1 plus x square, right? So this is your value. So what will be that value? 1 point, so this is 0.3542. okay, so you have three values. You can use Simpson's 1/3 rule to get the final value or integration value. I is equal to 1/3 1 plus 0.120 plus 0.3542. Therefore I is equal to 1.5128. 1.5128. Sorry, that was the previous answer. The answer would be 1.1418. So if you calculate this answer, you will come out to be 1.1418. So if you see, let's see what is the error now. So error is 1.216, that is your I true value that you have got here, right? Minus 1.1418. So error is now 0.0741. so it's reduced down by factor of 10, right? So it was 0.29 and now it's 0.07. so is a factor of 10 reduction is there. So Simpson's 1/3 rule, even if you are using the one formula, you are getting the value. So your steps, number of steps are same, but you are getting the better result. That's the takeaway, right? Now what it is saying, you use two applications of trapezoidal rule. So here we use the a single application. So if you want to consider two applications, you have to consider two segments or two intervals. So those two intervals would be like that. But in Simpson's rule, what we did is we applied the whole formula for the whole region, but we will not do the same for a two application trapezoidal rule. For this first interval, we will apply a trapezoidal rule. For a second interval, we will apply a trapezoidal rule and then add them up. So I'll just write down what I have explained. So trapezoidal rule, two applications, right? Two applications means apply it twice, means you have to use two intervals, because this rule is only applied for a single interval, trapezoidal rule. So if you have a curve like this, and you're going from 0 to 2.7, this here comes the 1.35, the midpoint. Now what you will do is, and this is your f1, f2, f3. So what you will do is, you will first apply trapezoidal rule here. We will call it I1, and this will be h by 2, f1 plus f2. Then you will apply a trapezoidal rule here. We'll call this I2, which will be h2 divided by f2 plus f3, and you will add them up to get the value of I. So we have f1, f2, f3, but how we use them in the formula is different. Now what happened is, you have two steps. You have to first apply it here, then apply it there, and then add them. So I is equal to I1 plus I2, therefore I1 is equal to h by 2. So h is what now? This is h. So h would be 1.35. h by 2, f1 plus f2. So that is h is 1.35 divided by 2, f1 is 1. So that in the previous question we have calculated f1, f2, f3, so we don't have to calculate them again. f2 is 0.3542. So let's get my calculator. This is 0.9140. I2 is h by 2, f2 plus f3. So 1.35 divided by 2, 0.3542 plus what is the 2.7? 0.12, right? 0.12. This is 0.3200, and if you add them up, you will get the final value. That is 1.2345. Okay, this is the way you get the final value. So what is the error would be? Error would be 1.216, that is your true value that we calculated analytically, minus 1.2345. So error is 0.0185. So if you see, you are using the same method, trapezoidal, but using it twice for a two different equidistance interval, and we are finding out the area under the curve, and the error is now drastically reduced. So from 0.296 you are getting very close to the value 0.0185. So this is the way the more number of the intervals you will get the better result. Now the one question arises, can distance of interval be different? Of course it can be different, but then you have to consider h value accordingly. So if you consider first interval at 1 and then you consider 1.7 as a second h, then h1 would be different, h2 would be different, and then you will calculate. So that call you take according to the function you are working with, and so on. But at the start you always do a midpoint. Then you go for a different varieties of it. So this is a 2 application. Now last one is single application of a 3/8 rule. So 1/3 3/8 rule. Now Simpson's rule 3/8 rule is used for interval of 3. So trapezoidal rule is given by n is equal to 1. This is for n is equal to 2. This is for n is equal to 3. So you need a 3 intervals. So 3 intervals means from 0 to 2.7, 3 intervals mean each interval of 0.9, right? 0.9 plus 0.9 plus 0.9. So your h would be 0.9 in this case. Again the logic the same for 3/8 rule, single, right? Let's say you have a curve like this. Now let's we want to go from 0 to 2.7. So in 1/3 rule you had midpoint, right? Now 3 equidistant. So this is 0.9, 1.8 and 2.7. So this is your h1, h2, h3 all are same equal to 0.9. So these are again f1, f2, f3, f4, and 1/3 rule is I is equal to 3/8 rule. Sorry, 3/8 rule is I is equal to 3/8 into h. f1 plus is 3f1, f2 plus 3f3 plus f4. f1 plus 3f2 plus 3f3 plus f4. So these are f1, f2, f3, f4 and h, you know. So now we have to find out f2 and f3 because they are different. f1 and f4 we know. So f1 is equal to f of 0 is 1, f of 4 is equal to f of 2.7 is equal to 0.120, 0.120, f of 3 is equal to f of 0.9. f of 0.9 is 1 upon 1 plus 0.9 square. So what is that? 1 plus 1.9 square is 0.5524, 0.5524, and f4 is equal to f of f4 is already found out. We have to find out f2 and f3. So this was f2 and now f3. f3 is f of 1.8. Is 1 upon 1 plus 1.8 square. So the value would be 0.2358. 0.2358. So if you substitute these values in this equation, you will get I is equal to 1.1762. Therefore, error would be 1.216 minus 1.176. This 0.0398. So even if the Simpson's trapezoidal rule, if you have to apply twice, you will get a better result here. So this is not the universal case, this happened because of the problem, but what is a general takeaway is, in Simpson's rule and with her 3/8 rule, Simpson's 1/3 rule, even if you are considering a more number of intervals, you will get the answer in the one go. In trapezoidal rule, it can only be applied in a single interval. So if you are considering the more number of intervals, you have to apply it more times and then add them up. So this is the first question. We'll go into the second question. Repeat the calculation of integral in the Q1 using a trapezoidal rule, but with a step size of h.3. Also, report the absolute error between the numerical value and the true value. So what it is telling you, what we did in the trapezoidal 2 application, we did at the midpoint. Now it is telling you h value. So h value is what? 0.3. Since h is equal to 0.3, right? And final value is what? A is equal to 0, B is equal to 2.7. Therefore, N is equal to B minus A by H. So 2.7 minus 0 divided by 0.3, that are 9 intervals. So here you will have a 9 intervals. So 9 intervals means you have to apply trapezoidal rule 9 times and you will get a 9 values, and then you will have to add them up to get down to the final value, right? So it's better way we construct this thing, table. So what is this thing f of x is 1 upon 1 plus x square, right? So you will basically go from x is equal to, so for this purpose what he is asking you, you are going from 0 to 2.7, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 3, 4, 5, 6, 7, 8, 9. So these are the 9s equidistant. So don't go on my this one, but they are equidistant. So the value of each interval is same h, that is 0.3. So this is 0.3, then 0.6, then 0.9, and so on till 2.7. Apply I1, I2, I3. So apply it 9 times and add them up to get down to the final value, and then calculate the error. That's what the question is. So what we will do, we'll do it in a tabular form. So x is from 0, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.7. F of x is the value you will get from this. So what value you will get? So for first one, I'm just writing it down. 1, you do it on your own pace. 0.9174, 0.7352, 0.5524. So I'm doing for 1.2. What I'll do is, the question is, I'm using 1 upon 1 plus 1.2 square, and I'm then writing it down. So that is 0.4098. Similarly for 1.5 it is 3.3077. For 1.8 it is 0.2358. For 2.1 it is 0.1848. For 2.4 it is 0.1479, and for 2.7 it is 0.1206. So what I have done here, I have taken the endpoints, interval endpoints, and I just substituted into the function value and got it function value. Now what our formula for this thing is? The trapezoidal rule. From trapezoidal rule, I is equal to I1 is equal to F1 plus F2 divided by 2. H by 2 into F1 plus F2. Similarly, I2 is H2 divided by F2 plus F3. So this is F1, this is F2, this is F3, and so on till F9. Sorry, F10, right? Yeah, F10. So these are 10 data points: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points and 9 intervals. So from each interval you will get like this till I9 is equal to H by 2 F9 plus F10. Get it? So how you will get it? From F1 and F2, if you substitute this value, H value is what? 0.3, you know. From this 2 point you will get here. 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 So these are your I values. So these values are 0.2876, 0.2876. Here you will get, this is I1, I2 is 0.2479, I3 you will get as 0.1932, I4 is 0.1444, 0.1443, I5 is this 2, I5 is 0.1076, I6 0.0815, I7 0.0631, I8 0.0499, I9 is equal to 0.0402. So these are your I9 I1 to I9 values. If you sum them up, you will get that is what is your the summation from 0 to n. What the value is 1.2155. So this is your final value 0.2155. So then error becomes 0.216 minus 1.2155. So that is very low, right? 0.216 0.0005. See, it's 10 raised to minus 4. So it's very low, right? So the more number of intervals, the error is very low using a simple trapezoidal rule. Now we'll go for a next question. So first question is done, second is done. The third question is use Richardson's extrapolation to compute the value of integral in a question 1. Also report the absolute error between the numerical value and true value. So what numerical Richardson extrapolation is? So in what we did here, in Q1 we solved it using a single application of trapezoidal rule, but also using a two application of trapezoidal rule. So we have used the single application and two applications, that is using a one interval and using a two intervals of a trapezoidal rule. So what your Richardson formula is, it says I true is nearly equal to, so in Richardson extrapolation, what we do is we have a solution using the same technique for a different number of intervals. So n is equal to 1, n is equal to 2, n is equal to 3, and so on. So for trapezoidal rule we are using, here we have n is equal to 1, n is equal to 2, and it tries to reduce down the error, or it tries to increase the accuracy. So you have to have a two solutions of using a trapezoidal method here. So I true is nearly equal to 4/3 of h/2 minus 1/3 IH. Excuse me. So what I was saying, so according to Richardson extrapolation formula, I true is 1/3, 4/3 of integration value using h by 2 and 1/3 using a h. So what h by 2 means? 2 applications, and this is 1 application. So we already have these values, so therefore I true is nothing but 4 by 3 into what is the value using a 2 application 1.2345, right, using a 2 application point 1.2345 minus 1/3 using a 1 application. So 1 application it is 1.5128. So therefore I true is 1.1417. So this is using a Richardson extrapolation. So therefore error is 1.216 minus 1.1417. .0743. So if you see, there is an improvement as compared to the Simpson's 1/3 as compared to what we got using only one interval, and right. So Richardson extrapolation basically reduces the error between your your true value and expected value. However, for this you require readings or a solution at using a 2 applications or 1 application as your formula requires. So it is reducing down the error between 2 values. Now for a question 4, repeat the problem in a Q1 using a this is I guess from this is typo question, I guess. So order of accuracy, right? So sorry for this was the question we already discussed in the previous session, so we need not discuss this. So this is from numerical differentiation. So this question has been already discussed in the previous class, so you can go and check that out. So we'll go forward. So compute the integral using 2-point Gauss Quadrature for the problem in the Q1. Perform a change of variable using y is equal to x divided 1.35 minus 1. So what happens is, we have some integral right here from, let's say, a to b. We'll convert it to the integral from -1 to 1. It's a quadrature, we're considering a quadrature between that, and we'll convert this function to those integral values, and then we will solve using a Gauss Quadrature 2-point formula. So it has said that use 2-point formula. So for that the formula is already defined, that I will tell you. First, what we have to do, we have to convert our integral limit from 1 to -1 to 1, whereas right now they are from 0 to 2.7, right? And it has already been told you to use y is equal to x divided by 1.3 minus 1 to change this. So it's already been told you what to do, you don't have to even do that. So we'll just start with y is equal to I. What is your I is integration from 0 to 2.7, 1 upon 1 plus x square dx. Now change of variable, this told you to use y is equal to x divided by 1.3.5 minus 1. So therefore x is equal to 1.35, will go that side, and then 1.35 y plus 1. This is your x. Therefore dx is equal to 1.35 dy. So your integrand becomes, so first you have to see what are your limits, right? At x is equal to 0, y is minus 1. If you put 0 divided by, so basically you are getting into that form that you require for a quadrature formula. Lower limit minus 1, upper limit, if you put x is equal to 2.7, it will be 2.7 by 1.35 minus 1. 2 minus 1 is equal to 1. So lower limit minus 1, upper limit 1. Therefore I becomes I quadrature, that is from 1 to -1 to 1. dx is what? 1.35 dy divided by 1 plus x square. So x is here, 1 plus 1.35 square into y plus 1 square. Okay, so this is your I quadrature. So whatever you will do from this point onwards, you will do it on this integrand, not on that one, because for a Gauss quadrature the formula, the integrand should be from -1 to 1. So it has already told you to use 2-point Gauss quadrature. So 2-point Gauss quadrature, how you get it as, so 2-point Gauss quadrature formula is the value of this I quad is given by using 2-point Gauss quadrature formula. The value of integrand is given by f of -1 divided by √3 plus f of -1 plus 1 divided by √3. So what you have to do, you have to substitute y is equal to 1√3 into this equation first, then y is equal to 1 divided by √3 in this equation, and add them up, and then you will get the value. That's it. So -1 to 1, 1.3, it's not even integration, so f of this, right? So f of y, so this is your f of y, So this is your f of y. In that, first we will put y is equal to minus 1 divided by root 3. Then you will put y is equal to 1 divided by root 3 and add them up. So that is what is your 2-point Gauss Quadrature formula is. That's why you can do it. There is a 3 points as well. There is a 1 point as well. You can go and check it. So what's the function? 1 point. Sorry. Okay. So 1.35 divided by 1 plus 1.35 square minus 1 by root 3 plus 1 bracket square plus 1.35 divided by 1 plus 1.35 bracket square 1 divided by root 3 plus 1 bracket square. So if you put this value in a calculator, you will get the value as 1.2623. This is your I chord. So I'll just explain you what we have done. So in Gauss Quadrature method, what we do is we first change the limit of integration from 0, whatever the value we have given to you, to minus 1 to 1, because the Gauss Quadrature formula are only applicable at minus 1 to 1 only. To do that, here you have already been told what would be your substitution. So if you use this substitution, automatically you will get the limits as minus 1 to 1. So your integrand would change from 0 to 2.7 1 from 1 upon 1 plus x square to this minus 1 to 1 f of y dy. So use 2-point quadrature formula tells you use minus root 3 into function value and substitute 1 upon root 3 into f of y value, get the value, add them up. The addition will give you the final integration value of the integrand that you were started with. I hope you clear with this. So this I 1.2623 is for whatever the I we were considering. Therefore error is 1.216 minus 1.2623, that is 0.046. So this is also one way. So Gauss, we started with three methods that were derived from Newton-Cotes. So that is Trapezoidal Rule, 1/3 Simpson's Rule, 3/8 Simpson's Rule. Then we saw how to reduce error between if you how to reduce the error or increase the accuracy of the results if you have a result at a different integral different trapezoidal rule value, if you have applied it for a different interval limits for trapezoidal rule. And now what we are doing is using a quadrature formula. So in the first three, there were different methods that were derived from Newton-Cotes. So Newton-Cotes is a generalized formula. If you apply for n is equal to 1, you get a trapezoidal. If you apply for n is equal to 2, you get a Simpson's 1/3. If you use n is equal to 3, you get a Simpson's 3/8 rule. Now here this is a altogether different way. It is changing a limit of integrands from whatever you have given to minus 1 to 1, and then going down to the solution. Then it has a 1-point quadrature formula, 2-point quadrature formula, 3-point quadrature formula also. Here we have only discussed 2 points. So you can also solve it using a 3 point. For 3 point, there might be an addition of two numbers where this minus 1.3 and minus 1 divided by root 3 and 1 divided plus divided by root 3 would be some different value. So this is your quadrature. So now we will go to the final question. The final question is an engineering question. Actually, we had used this equation, I guess, in the 4th week or a 5th week. I guess in the 4th week. So again, it is a velocity of a free falling parachute is with the linear drag is given by v, where this is a velocity function, where g is 9.81. Use trapezoidal method to compute how the jumper travels during the first 6 seconds of a free fall. You have given mc and use h is equal to 1. So you have to go from 0 to 6, and he has told you use h is equal to 1. That is a is equal to 0, b is equal to 6, h is equal to 1. Therefore n is equal to b minus a upon h. That is 6 minus 0 upon 1, that is 6. So you have to use 6 intervals. 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. So this 6 interval you have to use and get down to the value. So what value you want? You want to find how far the jumper traveled. So you have to find the distance. So what is, if you have a time and velocity, so we know velocity is distance upon time, right? Therefore time is what? So therefore distance is what? Distance is velocity into time, and that is nothing but the area under whatever the curve it would be. So basically area under the curve means you have to find the integration of this velocity function that there would be. So whatever this velocity function would be, this is for a demonstration purpose. I don't know how the function would be looking like, but let's say this is a function of v, which is given by this equation here. So what we have to do, we have to find out the integration. Also, you know, s is equal to v dt. It's also, if you remember your +2 physics, s is equal to v dt, right? So here you have to go from a to b only. So what is your a? A is 0 and your b is 6, and then you have to use 1, 2, 3, 4, 5, 6. So I will be more. So these are the 6 intervals, 1, 2, 3, 4, 5. So these 6 intervals you have to apply trapezoidal rule here, here at a different one and get the value, right? So you need a what is a function of v, and then you will apply trapezoidal rule for a 6 times. So function of v is g into m. So g value is 9.81 into m is 80 divided by c 10, 1 minus e raised to minus c by m, that is 10 by 80 into t. This is your function. So your function comes out to be 78.48 into 1 minus my e raised to minus 1.125. So this is your function of V. Therefore S is equal to zero to 6, right? So that is nothing but your I1 plus I2 plus I3 plus I4 plus I5 plus I6. Now what are I1, I2, I3, I4, I5, I6? These are the value trapezoidal applied at the 6 intervals. So better way, you will use this thing, table. So table will give you a better picture, easier picture to solve this. So what is I1 for just people who don't understand? So H2. So what is your H? H you have already given as 1. This is F1, F2, F3, F4, F5, F6, F7, right? So this is F1 plus F2. I2 would be H by 2, F2 plus F3. I3 would be H by 2, F3 plus F4, and so on till I6 is equal to H by 2, F6 plus F7. So this can also be written in the tabular form in a much easier way. T, then we have V. From V we will find out X. So this is your summation of I or summation of I will come at the end, and H is what? 1. So you know that. So H is 1 since 1, so you have to start at 0, right? 0, 1, 2, 3, 4, 5, 6. So if you substitute what is the V, you have to put this 0 into this function of V. So if you put 0 here, you will get this value here. So if you put 0 here, so what you will get? This will become 0. So 1 minus 1, 0. So basically the value would be 0, right? So this is your 0. Similarly, if you put the rest of the values, you will get, for a 1 you will get 9.2216. For 2 you will get 17.3597. For 3 you will get 24.5415. For 4 you will get 30.8795. For 5 you will, for t is equal to 5, you will get 36.4727, and t is equal to 6, you will get 41.4087. So these are your function values. So these are your what, say f1, f2, f3, f4, f5, f6 and f7. Now you will substitute these values in this equation and get the value of x, right? So basically these two values will give you first I1 here using this formula. So h is equal to 1, you already know, f1 and f2 you know. If you substitute, you will get 4.6108, 13.2907, I3 you will get 20.9506. From these two you will get I4, that is 27.105. From this two you will get I5 as 33.6761. From these two you will get I6, that is 38.9407. So basically you are finding out the area under the curve for each strip, and now you will add them up to find the value of I, and that value would come as 139.179. So this is your I value, is nothing but your distance, that is S is equal to 139.179 meters. So this much distance he has traveled. So these are the all questions I had to discuss. We started with the Newton-Cotes formula, and then we discussed the three methods that are given by, or that can be derived from a Newton-Cotes formula. Newton-Cotes formula is generalization formula which is derived from a Newton's forward interpolation series. Okay, if the n is equal to 1, if you put in a Newton-Cotes formula, you will get a trapezoidal rule. If you put n is equal to 2, you will get a Simpson's 1/3 rule. If you put n is equal to 3, you will get Simpson's 3/8 rule. For a Simpson's trapezoidal rule, it is only applicable in a single interval. For a 1/3 rule, you require 2 intervals. For a 3/8 rule, you require 3 intervals. You can use a trapezoidal rule for a 2 interval or 3 interval or more intervals, but just you have to repeat the process and get to the value. Now if you have 2 values at using a 1 interval and a trapezoidal rule and 2 intervals of a trapezoidal rule, then you can use a Richardson extrapolation to find out a better result. It reduces down the accuracy. Then the quadrature, in the fourth question we saw the quadrature, Gauss quadrature. So Gauss quadrature is a different from the previous question techniques that we had discussed. It is not related to Newton-Cotes. In that, what we do is we basically change the limit of integration from whatever the limits of integrations are to -1 to 1 and solve it using the direct formula that has been given to you. So here it has been told you to ask you to find out using a 2-point Gauss quadrature. So you must know the formula, what substitution you have to do, and then you will get the integration value. And the final one was a practical engineering example where we found out the value, how much distance the parachute traveled by the velocity values calculated using a function at different time intervals. So this is what I had to discuss today. We will meet in the next class in the next week, Tuesday 7 to 9. Thank you.